This is the last of the videos for this unit. We are now going to talk about what's happening with those shared electrons between the two atoms in a covalent bond. Now, just like having an older brother or sister or anybody, when you say share, it could be a very broad definition. So for example, I have an older brother. My mom would tell him to share his candy with me or something like that. And let's say he has 10 M&Ms and he shares one with me. So he gets 9 and I get 1. Technically, he shared, but did he share fairly? No. If he had shared complete, he would have had 5 and I would have had 5. So there's a difference in the word share based on how you look at it. So the same thing is happening in a covalent bond. Sometimes elements are sharing fairly and sometimes they're just sharing a little bit. So we've got to know the difference between those two things. So the first thing we need to look at is electronegativity. We've talked about this word in previous unit with the periodic table. Remember the trend for electronegativity, if this is the periodic table, increases up and to the right. So the elements that are the furthest up and to the right have the most electronegativity. Except, remember, group 18 has 0 electronegativity. They don't want to share or even get electrons. They're happy the way they are. So electronegativity is the ability of an atom to attract electrons in a chemical bond. The type of bond formed is largely determined on the difference in electronegativity. Now I know you can't really see this well in the video, but it is in your notes. So if you have electron or electronegativity difference 4 to 1.7, then it's ionic bond. Excuse me. Okay, so if there's a huge difference between electronegativity, it's ionic. Because remember, one element is giving the electrons away and the other's taking it in. There's no sharing going on, so it's going to be a big number. If it's between 1.7 and 0.3, it's called polar, which we're going to talk more about what that word means in just a second. Below 0.3 or 0 is going to be nonpolar. So if I give you a value, electronegativity difference value, you should be able to tell me what type of bond it is. Okay, nonpolar means no poles. So a magnet has a north and a south pole. There's a huge difference between those two poles. And they even, if you put a north with a south, they attract. So the piece that you've got to get is nonpolar means no poles. So that means there's not going to be any kind of north or south formed. Everybody's going to be happy. So the electrons are shared equally. So this is where my brother shares 5 M&Ms with me and he gets 5. Everybody's getting the same thing. So therefore, there's an equal charge distribution. Everybody's getting the same stuff. And this is showing you that. So if you look at chlorine, Cl attached to Cl, chlorine is chlorine, so there's no difference in electronegativity. So everybody has the electrons like they should. But if you compare hydrogen and chlorine, chlorine's a hog. So therefore, if you picture the electrons are being pulled towards the Cl, which causes this difference here. So a polar covalent bond, the electrons are not shared equally. So this is where the whole candy thing, I get 1 M&M, he gets 9. Yes, he can go and tell my mom he shared with me, but not quite like she was probably wanting him to. So the atom with the higher electronegativity draws the electrons towards itself. So whatever has the highest electronegativity, meaning it's the furthest up and to the right, is going to be the atom that pulls the electrons in. And then the other atom is losing that electron. So therefore, there's an unequal charge distribution. So for water example, oxygen is furthest to the right, so therefore oxygen is going to be electron hog. So when this happens, it causes water to have a partial positive charge and oxygen to have a partial negative charge. So, example, HBr. if you draw the bond, it just looks like that. So hydrogen has electronegativity of 2.1, bromine has a charge of 2.8. Bromine is furthest up and to the right, so it has a higher electronegativity. This results in a polar bond. Now, you show the electrons being pulled towards bromine by drawing an arrow with a line through it. So it looks like a T with an arrow at the end. This is showing you that the electrons are being pulled towards bromine. Now, when this happens, it causes a polar bond. So bromine is being the electron hog, so electrons are negative. This means bromine is going to become slightly negative. Now, the symbol for this is an unfinished 8. So you start to make your 8, you come to where you're about to cross over and stop. So you have an unfinished 8 and a negative. This means partially negative. Then you get hydrogen. Since bromine's being the electron hog, that means hydrogen's not getting all the electrons that it needs. So it becomes slightly positive. Now, when you get a bunch of these together, with all these partial positive and negatives, you get more attraction between the actual molecules. Now, can you have a nonpolar molecule with polar bonds? The answer is yes. Because, looking at BF3, if you have boron in the middle and all the fluorines on the outside, which fluorine has the highest electronegativity, and all of those fluorines are pulling on the electrons the exact same way, it's like a tug of war where nobody's moving. Those electrons are not going to go anywhere. So therefore, if you have a symmetrical formula or symmetrical compound, when you draw it out, it is a nonpolar molecule. This is the key to this. You have a nonpolar molecule if and only if. So both of these two things have to happen. There are no unshared pairs on the center atom. So as soon as you see leftover dots on that center atom, you know that the molecule is polar. All surrounding atoms must be the same. If they're not the same, then it is polar. Okay? If one of these two things is not there, okay, it is polar. So, for example, let's go back to this. So flip to this page in your notes. You should see another column on the side here that says polarity. I don't have that column up here, so I'm just going to write it here. Okay? But when you write the answers in your notes, you need to write it in that last column. So we're going to look at two things, okay, what the video just said, or what I just said. First, in order to be nonpolar, there can be no leftover dots on the center atom, and all the surrounding atoms must be the same. So, looking at this structural formula, first thing, are there any leftover dots? No. Check. We got that one. Are all the surrounding atoms the same? Yes. So therefore, this one is nonpolar. No leftover dots, and the surrounding atoms are the same. Next, BCl3. First, are there any leftover dots on the center atom? No? Good there. Are all the surrounding atoms the same? Yes. So therefore, this one is also nonpolar. Next, are there any leftover dots on the center atom? Yes. Therefore, this is polar. Anytime there are leftover dots on that center atom, it is automatically polar. Now, the other example that I don't have one specific on the slide is the surrounding atoms. So, for example, if I had, let me go back to this. I'll draw it right here. If I had this, Okay, you might want to draw this example as well in your notes. Is this polar or nonpolar? So again, to be nonpolar, there can be no unshared pairs on the center atom, and all surrounding atoms must be the same. There are no leftover dots, so we're good there. Number 2, are all the surrounding atoms the same? No. We have bromine here. The rest are hydrogens. Therefore, this is polar. We will be doing more practice with this. With polar bonds, we get what's called an intermolecular force. Now, intermolecular means that they are occurring between your compounds, okay? They are occurring between compounds. Not within, between. Keyword between. Ionic and covalent happen within the compound. Okay? So therefore, intermolecular forces are weaker than your ionic and covalent because they are between compounds. Ionic and covalent are within the compounds. So intermolecular is between. Ionic and covalent, they're called intra. Intra means within. So intracovalent or intramolecular forces. Pretty much with these, you just sort of need to know what they are and their strength. So these two are called van der Waals. I'm not so much worried about the word van der Waals as I am actually knowing what I had in gold here. So dipole, not dipole, dipole interactions occur between positive and negative ends of a polar molecule. So if you have a partial positive and a partial negative, they're going to be attracted to each other. London dispersion. Same thing, except for they are temporary. Since they are temporary, they are the weakest type of intermolecular force. So if you think about London bridges falling down, same thing, weakest, so they're falling apart. Then you have hydrogen bonding. Hydrogen bonding obviously has to be an intermolecular force that contains a hydrogen. And it is the strongest type of intermolecular force. So intermolecular forces cause a strong influence on the boiling points of a substance. So these intermolecular forces are changing the properties of your compounds. So in this picture, and I'm going to draw it for you as well here because I know the picture can look somewhat crazy. So if you draw the water molecule, okay, if you want to actually draw it, because I know this picture isn't in your notes, this is what it would look like. So you have one water molecule. Oxygen has a stronger electronegativity, which is going to cause it to be partially negative. This hydrogen then is partially positive. Now when you have a glass of water, you don't just have one molecule of water in there, okay? So therefore you're going to have another water molecule. Bring in another one. They're surrounded by each other, right? So what's happening in this water molecule as well? This oxygen is partially negative. This hydrogen is partially positive. I mean, this one is too, okay? All the hydrogens are partially positive. So what ends up happening is you have these partials all over the place, so they're going to become attracted to each other. This partially positive hydrogen of one molecule is attracted to this partially positive oxygen in the other, which therefore gives water a sticky property. So for example, a waitress trying to pour a glass of water, and you may or may not have seen this, but I've seen it a lot of times. A waitress trying to pour some water out of a pitcher sometimes spills because water molecules stick together. Okay, so once that water starts flowing out of the pitcher the wrong way, it's going to keep on going. Okay, and I'm going to do a demo in class that'll show that even more as well. So the main thing you've got to know from this is the strengths of the intermolecular forces. So London dispersion is the weakest, dipole, and then you have hydrogen bonding as the strongest.